Welcome to Number 9 Squadron online training, based here in Wanganui. It's really great to have you along. Today's session is based on aviation training. We will be learning about different aircraft engines, and in today's lesson we will be covering combustion engines for propeller-driven aircraft such as the Cessna 152 and the 172, radial engines for propeller-driven aircraft such as the Boeing Super Fortress and the Corsair, and jet engines for turbojet aircraft such as the Boeing 737 and Airbus A330. The objective of this lesson is to understand how each engine works to create thrust for aircraft. The need to ensure you have the best possible understanding and experience when flying aircraft. References can be found on any civil aviation websites. We encourage you to take notes during the videos as we will have a question and answer session at the end. Enjoy the training, let's get started.
A basic lesson in the fundamentals of a four-stroke EFI gas engine may be helpful to your understanding of Mercury products. Here are the basic components of every four-stroke gas engine: a piston, a connecting rod, a crankshaft. As the piston travels up and down in the cylinder, this lateral motion is turned into a rotating motion at the crankshaft. The longer the stroke of the piston, the larger the displacement of gas and air occurs in the cylinder. To propel that piston, we need to ignite a tiny bit of gas and a whole lot of air. This creates expansion inside the cylinder. The fuel delivery system consists of an air intake manifold, valves, intake and exhaust, a fuel injector, and a spark plug. A four-stroke engine is called a four-stroke because 4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke. The fourth stroke is the exhaust stroke. As the piston travels upward, the exhaust valve opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again. It takes 1 up and down motion or 2 strokes of the piston to create 1 revolution of the crankshaft. RPMs, or revolutions per minute, is how many times the crankshaft rotates within that minute. At wide open throttle, the crankshaft may turn at 5,000 RPMs, or a dizzyingly 83 times per second. Meanwhile, the piston traveled up and down 166 times in that same second. Want to see how fast that is? Now, that's fast. Let's see it again. Amazingly, the four-stroke EFI engine does this smoothly, quietly, and reliably for years and years of operation.
How does a radial engine work? And the answer is just about like every other reciprocating engine. It follows a four-stroke cycle. The first stroke is the intake stroke, and that's where the downward moving piston sucks the fuel air mixture through the intake manifold and the intake valve. Then, as the piston begins to move up, it compresses that mixture in the compression stroke. Right before the piston hits the very top, the spark plugs fire, and those sparks start burning the fuel air mixture, causing the gases to expand and forcing the piston back down in the power stroke. And then the crankshaft starts spinning the piston back up to the top, forcing out the burned fuel air mixture in the exhaust stroke. If you're looking at a radial engine from behind, as you would from the pilot seat, you'll find that the cylinders are numbered in clockwise order. So on this engine, they'd be numbered 1, 2, 3, 4, and 5. And a radial engine follows a very specific firing order. Here, you alternate cylinders. So it would be 1, 3, 5, 2, and 4. Radial engines were used because they could generate a lot of power and they were really simple. They had very short crankshafts, which could be very strong because you really didn't need a lot of length between your prop and your cylinders, and you could fit up to 9 cylinders around your crankshaft. However, as time went on, 9 cylinders didn't give you enough power, so we started to add more and more rows of cylinders. In fact, the Wasp Major had 4 rows of 7 cylinders for a total of 28 cylinders. It was used on the B-36 Peacemaker, which had 6 Wasp Majors pushing propellers and 4 turbojet engines. The slogan was originally 6 turning and 4 burning. The Wasp Major had a problem. It didn't cool really well. As the air moved past the first row of cylinders, it did a great job, but it got warm, and so each successive row of cylinders was less efficient at cooling. And the Wasp Major had a tendency to catch on fire. So crews gave it a new nickname: 2 turning, 2 burning, 2 smoking, 2 choking, and 2 more unaccounted for. At the end of the day, turbojets replaced the radial-powered piston engines simply because they were much more reliable and they could generate a ton more horsepower. But that's a lesson for another day.
I'm Jake O'Neill, creator of Animographs, and this is how jet engines work. Most jet-propelled airplanes use a turbofan design. The turbofan can be thought of as a high-tech propeller inside of a duct called a diffuser, driven by a gas generator. The core. The core of a jet engine is a gas generator that creates high-pressure gas to power a turbine. This setup has compressor, combustor, and turbine sections. The compressor. Compressed air makes for a much more powerful combustion reaction relative to engine size. Compression happens in stages that force incoming air into an increasingly narrow chamber. A single compressor stage is comprised of a spinning rotor paired with a ring of stationary stator vanes which are attached to the core casing. Rotor blades swirl the air as they force it through the compressor. Stator vanes slow this swirling momentum in exchange for increased air pressure. The compressor has 4 low pressure and 10 high pressure stages. The combustor. Air is mixed with fuel and ignited as it passes through the combustor, releasing a jet of super high-powered gas. The design shown here is an annular combustor, meaning ring-shaped. Compressed air enters the inlet nozzles. Each nozzle is coupled with a fuel injector and is designed to swirl the incoming fuel and air for an even mix. A couple of igniter plugs, not unlike the spark plugs found in car engines, ignite this mixture, and the reaction spreads evenly around the ring. Once started, combustion continues as long as air and fuel are supplied. The turbine. Turbines at the rear of the jet engine are powered by exhaust gases exiting the combustor. Much of the turbine power is used to turn the fan, while a smaller percentage powers the compressor stages. Turbine fins get extremely hot. Some air from the compressor is diverted for cooling, and special coatings are used to keep temperatures down. The exhaust cone is specially shaped to mix and accelerate exhaust streams. It also covers sensitive internal engine parts. The fan. Early jet engines were turbojets, where all incoming air flows through the core. Most modern winged aircraft engines are turbofans, where only a fraction of air enters the core or gas generator, and the resulting power turns a specially designed fan. Again, the fan can be thought of as a high-tech propeller inside of a duct. Air that does not enter the core is called bypass air. High bypass engines are designed to move large quantities of air at slower cruising speeds, a range of about 310 to 620 miles per hour. The exchange for high efficiency is engine size. High bypass engines can be very large, with massive fans compared to core size. Commercial airliners or military transport aircraft are example applications. Exhaust velocity is a major factor in jet engine noise. High bypass engines surround fast-moving core exhaust with large quantities of slower-moving bypass air for quieter operation. Military fighter aircraft use low bypass engines which are more compact, have high power to weight ratios, plus supersonic and afterburner capabilities, in exchange for things like poor noise control and high fuel consumption. Afterburner. High-performance engines may have afterburner capability. Additional fuel is sprayed into a jet pipe section where it mixes with exhaust gas and is ignited, producing a second stage of combustion. Since afterburner is fuel inefficient, it's generally used in short bursts during takeoff, climb, or combat maneuvers. The exhaust nozzle is adjustable for maximum exhaust acceleration and to avoid undesirable back pressure, which can harm forward engine parts.
That completes today's training on common aircraft engines, but before we go, let's have a quick quiz and see how you got on. The objective of this lesson is to understand how each engine works to create thrust for aircraft. The need to ensure you have the best possible understanding and experience when flying aircraft. References can be found on any civil aviation websites. Thank you for participating with 9 Squadron Online, and we look forward to seeing you soon.